Hello everyone, I want to take an opportunity in this video to talk about the effect of substitution on cyclohexane chair conformations. So this is a follow-on from Dr. Davis's video about cyclohexane chairs and the conformation available there. We'll take a look at what the influence of substitution would be on those cyclohexane chairs. So if you haven't had a chance to look at Dr. Davis's videos, now would be a good time to go back and take a look at those videos just so you can kind of follow along and see what we're talking about here. And so what I want to do here is I'll just draw out cyclohexane with a substituent on it so we get a feel for what that's going to look like. So I'll start out by just drawing cyclohexane. I'll put a substituent on it here, the methyl group. Okay, and so now let's take a look at what the influence that methyl group might have on the overall chair conformation of that molecule. So what I like to do is I'll just draw a chair. So I'll draw a chair out, and what we'll do is we'll go through it on the iPad here. I'll draw some structures, and then we'll take a look with the model kit to see if we can follow along what we're drawing here as well. So again, I would suggest if you're playing along at home, you can draw these structures on a piece of paper and then see if you can visualize them with the model kit as well. So there's a cyclohexane chair. I want to put a methyl group somewhere, and what I like to do, if I don't know where to put anything, I'll just stick it on somewhere and kind of see what it looks like if I do that. So in this case, what I'm just going to do, I'm going to put that methyl group on the footrest of my cyclohexane chair, and I'm going to put it on there in a equatorial position. I'm drawing in explicitly the axial hydrogen on this chair. Okay, so on its own, does this tell us anything at all about the methyl cyclohexane? Well, the answer is no, not really. So what we'd like to be able to take a look at is what the other chair conformation shows us, and then can we get any kind of good understanding about what the conformations look like there. So what I'll do is I'll draw the other chair conformation, then we'll take a look at them with the model kit. And again, so Dr. Davis spent quite a bit of time talking about how these were in equilibrium, so I'll just draw a little pair of equilibrium arrows to go back to the structure that's on the other page over here. So this structure with the methyl group equatorial is in equilibrium with the other chair conformation. And again, what was the headrest now becomes the new footrest, and what was the footrest now becomes the new headrest. There, and so that's not a very good headrest, so I'll just make that disappear for now. There, so that's a little bit better. So now there's the other chair conformation with that methyl group sticking up axial. And so again, that's in equilibrium with this other chair conformation where that was sticking out equatorial. This footrest here has now become the headrest on the other page, and that headrest has become the footrest in this other conformation that we have access to. And again, look back at Dr. Davis's videos, you don't see what's going on here. And so now the question we want to sort of see if we can get a feel for is, what's the difference, if any, between these two conformations? And so before we come to that, maybe what I'll do is I'll just see if I can play along and show you on the model kit exactly what it is we're looking at here. Okay, so there's our model of methyl cyclohexane on the model kit, just as we kind of drew it a minute or two before on the page. We've got it here now in the model kit lying flat. We've got the cyclohexane ring, and there's our methyl substituent up at the top. And so now if I pick this up, like I said, I don't really know what to do with that substituent, so I'll just stick it out equatorial. And you can see that it's sticking out equatorial here in this position. And we can see now there's the axial hydrogen atom down below, and the rest of the ring is over here. And again, if you've gotten a chance to buy the model kit from the bookstore or from other sources, a really good opportunity to kind of see if you can make that, play along a little bit as we're doing this here on the video. So now, what's the other chair conformation that we have available to us with this particular ring system? Again, I'll grab that footrest and twist it up, and grab the headrest and twist it down. So there's the other chair conformation that we have available to this molecule, where that methyl group is sticking up axial. Methyl group is sticking up axial, and the other hydrogen atom that was axial is now equatorial. And so the question you kind of ask a little bit as you're flipping back and forth between these two chair conformations is, well, do they look the same or do they look the different? In cyclohexane, they were identical. Here, do they look the same or do they look a bit different? And I would say, for example, if you look at what that methyl group is interacting with in that equatorial position, there's nothing for it to interact with at all. Right? If you visualize that methyl group as a cloud of 6 electrons that are holding those 3 protons onto that carbon atom, it's sticking out into space. It's just kind of nothing at all on the molecule itself, on the rest of the molecule it's interacting with. But if I flip that up into the axial position, now what you can observe is that this methyl group is sticking up in an axial position, and it's very close to these 2 protons on the other side of the ring that are also axial. And so we get these axial interactions. Call them 1,3 diaxial interactions, as the book calls them. So these 1,3 diaxial interactions. And so to me, and I think hopefully to you, that looks different than the equatorial conformation where it's not interacting with anything at all. And so if we have parts of our molecule interacting, we often observe that that results in an increase in the energy of that conformation. Well, how much of an increase in energy of that conformation would we expect? Well, if we take a look again at that conformation drawn out, what we observe is that these hydrogens here, I'll draw it in black, these hydrogens here are sticking straight up, and they have this interaction with this methyl group in that axial conformation. That's something that's missing in this equatorial conformation. So what's that energy penalty? What do we observe? And again, this is an observation that we make. This is a measurement we can make on this molecule. And we can observe that this conformation where that methyl group is axial is actually higher in energy than the conformation where that methyl group is equatorial. So what's that energy penalty? What's that interaction cost? Again, that interaction costs in terms of energy, and again, we look in free energy, delta G, not the free energy, and we'll come back to this a little bit more in chapter 6, but the difference in energy between the equatorial and the axial conformation here is minus 7.6 kilojoules per mole, minus 7.6 kilojoules per mole. That is the equatorial isomer, conformation, the equatorial conformation where that methyl group is sticking out is lower in energy than the one where that's sticking up in an axial position by 7.6 kilojoules per mole. Now again, you might be saying, well, so what's the big deal here and who cares? It's just a bit of chemical trivia, but that's a pretty big difference in energy for things like conformations. What the result of this is that at room temperature, so 95%, at room temperature, 95% of methyl cyclohexane is sitting in that conformation, in this conformation where that methyl group is sticking out in that equatorial position. So that has a big influence, just that small energy difference has a bit of a big influence on this. And this is all purely sterics. So it's all purely sterics with that 1,3 diaxial interaction between the 2 methyl groups on carbon atoms that are 3 atoms away from that methyl group, but they still have enough of an interaction that we can observe this energy difference between the 2 of them. Okay, so now the question you might be asking is, what's the influence on this difference between the 2 chair conformations if we make that substituent a little bit bigger? Well, let's take a look at that next. Let's take a look at what the influence is if we go from a methyl to an ethyl group. From a methyl group to an ethyl group on methyl cyclohexane. Well, let's take a look at the 2 chairs that we can draw here, and I'll see if I can fit them all on one screen to see if we can get them a little bit more now that we've got some more practice at drawing chair conformations. My equilibrium arrow there, just kind of cramming it all in place. And so there's those 1,3 diaxial interactions across that chair. Across that chair, I'll get the chairs a little bit better as I sort of figure out this stylus. What's the interaction here for ethyl cyclohexane? What's the interaction here? Now, it's not much different, as you can imagine, just by looking at this than what we've observed with the methyl. We've replaced one of the hydrogens with a methyl group in this particular instance, but it's pointing away from those key protons on the other side of the molecule, pointing away from the protons on the other side of the molecule. So you might wonder what the interaction is here. The energy difference isn't much bigger. That's 8 kilojoules per mole for that energy difference. 8 kilojoules per mole. And again, the result of this is that most of it's sitting in that equatorial conformation. We have 96% in that equatorial conformation. Okay, so then what happens if we go up one size slightly bigger? Well, let's take a look at that. We'll do another slightly bigger size here. This is a cyclohexane. With an isopropyl group on it. So now it's a little bit bigger, slightly bigger size there. And we can now draw the chairs. Again, one of the chairs where it's sticking out in the equatorial position. My equatorial or equilibrium arrows. And so now we've got a little bit more interaction here. We've got a little bit more interaction with these 1,3 diaxial protons over here, because now we've got this methyl group that can't quite totally twist out of the way. So if you look at the conformations around that carbon-carbon bond, you can see that there's a bit more interactions. And maybe I'll see if I can show you this or convince you of this with the model kit here. So again, there's the isopropyl cyclohexane that we have. So I twist that right way around. There's the isopropyl cyclohexane that we have. And again, if I lift that up and put that out equatorial, you can see that that substituent is sticking out into space and not really interacting with anything at all. And if you've got your model kit and you're playing along at home there, you can see that there's plenty of space for that to rotate around out there. Now, if I flip to the other conformation, the chair conformation where that isopropyl group is now axial, you can see that there is free rotation or rotation around that carbon-carbon single bond. And so there is a conformation that carbon-carbon single bond can adopt where there's only a single proton pointing towards the 1,3 diaxial protons on the other side of the molecule. And so it can get itself out of the road, but every time it twists around, one of these big methyl groups is coming in to interact with those protons on the other side of the molecule. And so that raises the energy of these interactions a little bit. Let's see how much of energy penalty that generates. So here in the isopropyl version of this, that energy penalty by those 1,3 diaxial interactions is a little bit larger than it was in the ethyl group here. The observed, and again, this is an observation, we can measure this. We won't tell you how we measure it. Come back next year for those experiments, but how we measure that delta G here. .2 kilojoules per mole is the energy difference between the equatorial conformation and the axial conformation. So what influence does that have? That means at room temperature, 98% of isopropyl cyclohexane is in the equatorial conformation. That is, 98% of it is sitting in this conformation here where that isopropyl group is sticking out into space and not interacting with anything. It sounds like a lot, but still 2% is still something significant. And we'll see in some experiments some reactions that we'll talk about in chapter 7, that we can still see some product of that 2% reacting in particular reactions. Okay, so now you might be asking, well, what happens if we make this substituent even larger? Well, let's take a look at the ultimate substituent that we can make a larger. What if we replace that final proton with another methyl group? So there, I've replaced that with a methyl group. So I'll replace that with that isopropyl group with another methyl group on there, CH3, and let's see what this looks like now in terms of putting that on the chair conformation. Because that's such a big substituent, what I'll do is I'll just draw it out in full here. So there's that T-butyl substituent, tertiary butyl, and we'll use this a couple dozen, 100 times between now and the end of November. So you'll get used to hearing us talking about T-butyl group or tertiary butyl group. And so that T-butyl group is sticking out there on that ring in that equatorial position. And what's the other conformation that we have access to? And again, the other chair conformation of cyclohexanes are really the only one that we're interested in looking at. So now there is that T-butyl group, and as you can imagine, there's nowhere for those methyl groups to escape from in terms of interacting with those protons on the other side of the molecule. Not sure I made that any better. So there's no place for those to escape from that interaction on the other side of the molecule, so they're banging into those protons in a large steric interaction. Let me see if I can convince you of this on the model kit, just to give you a feel for what those interactions might look like, and then we'll look at the energy penalty that's involved. Okay, so on the table now we've got the T-butyl cyclohexane model that we've built. And so again, I'll just kind of pick this up and take a look, and there's that T-butyl group sticking out equatorial on that cyclohexane ring out into space. And you can see that that would rotate freely out in space there. It's no other part of the same molecule it's interacting with, no other intramolecular interactions. It's just spinning around, spinning around, spinning around. And so now the other conformation where that T-butyl group goes up axial, sticks up there. The other part of the cyclohexane ring comes down, of course, into the footrest. So now that T-butyl group is sticking up, and you can see as it spins around, those methyl groups are interacting directly with those protons on the other side. There's no escape there. In fact, if you spin it fast enough, you can get them to click together a little bit. If you're playing around with the model kit, you see there's no way that that conformation can escape that 1,3 interaction with these two protons on the other side. That just constantly interacts. So it much greatly prefers, we would sort of predict that it much greatly prefer to sit with that T-butyl group out in the equatorial position. So you can see that the model, it sits out there where there's nothing for that T-butyl group to interact with. So there must be, we would predict anyway, certainly a significant energy difference between the axial and equatorial conformation of T-butyl cyclohexane. Well, let's take a look at what we actually observed for that energy penalty. So we want to take a look at what the difference is in the energy between the equatorial and axial conformation. And what we observe, again, we observe this. Minus 22.8 kilojoules per mole. That's a lot. That's a very big, that's more than twice the difference between the two chair conformations that we observed with that isopropyl substituent. That's simply because there's no escape from sterics in this conformation that we have here. Those 1,3 diaxial interactions are large interactions that really bias the chair conformations towards this equatorial one. And so you might say, well, what's the big difference? Like, what's the deal? What's the big deal about this? What influence does that have? This means that at room temperature, the ratio of equatorial to axial is about 10,000 So about 10,000 in the equatorial to 1 in the axial conformation. That's a large, large difference. That's a very large difference. In fact, it's so large that what we say is that the T-butyl group locks the conformation of cyclohexane in that equatorial, so that the T-butyl group sits equatorial and locks the whole thing in position there. And so, again, you might be saying, well, what's the big deal? This is just some more chemical trivia. But it's not really. We're going to use this T-butyl group a lot in Chapter 7. We start looking at the outcomes of different reactions, elimination reactions, and even substitution reactions. We'll see that that T-butyl group has a big influence on the outcome of these particular reactions. So we'll come back to this, and we'll use this quite a bit as we get towards the end of the course. So for now, I'm going to leave it for this video. In the next one we'll post up, we'll talk about disubstituted cyclohexanes.